Hi, my name is Brian Caffo. I'm in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health, and this is Mathematical Biostatistics Bootcamp, Lecture 8 on asymptotics. In this lecture, we're going to take a trip to asymptopia. Asymptopia is a land where we have an infinite amount of data, so it should be fun. We're going to talk about limits, but limits of random variables. And so there's intricacies that you have to account for when you consider random variables instead of standard mathematical limits. And it's a quite difficult subject, but we're going to show that we have basically two tools, the law of large numbers and the central limit theorem, that are going to be our primary methods for looking at limits of random variables. So let me just review numerical limits first. And I'm not going to go into too much detail, and I'm going to kind of treat it heuristically. Just to illustrate, in case your asymptotics is a little bit rusty, suppose I had a sequence where A1 was 0.9, A2 was 0.99, and A3 was 0.999, and I hope you can get the pattern at this point. So clearly this sequence, in some sense of the word, converges to 1. It converges to 0.9999999. So that gets closer and closer to 1 as the element of the sequence gets larger and larger. Well, we can formalize this. The formal definition of a limit is for any fixed distance, we can find a point in the sequence so that the sequence is closer to the limit than the distance from that point on. So take, for example, this sequence. The distance between an and 1 is 10 to the minus n, where n is the point in the sequence. And so if we pick any distance, say epsilon, we can find an n so that 10 to the minus n is smaller than epsilon, and then because 10 to the minus n just keeps getting smaller as n gets larger, then it's smaller than epsilon from that point onward. So that satisfies our definition of a limit, so clearly this converges to 1. And it's kind of an interesting fact that an infinite sequence of 0.9s and 1 is the same number. But that's kind of an interesting fact that if you ever take a class on real analysis, they'll discuss that sort of thing at length. But anyway, I hope you get this basic sense of a limit. As n goes to infinity, the sequence converges or looks more and more like its limit so that the distance just gets closer and closer and closer and never gets bigger again. The problem with that is that that only works for just a series of numbers, right? Now we want to talk about, say, limits of averages of coin flips. And then it gets much harder. So take, for example, the average. And now we're going to talk about an average comprised of n observations. So let's say xn bar, and now instead of saying x bar like we typically do, which is our average, we're going to annotate it by a subscript n to show that it's an average of the first n of a collection of IID observations. So for example, x bar could be the average of the result of n coin flips, which is the sample proportion of heads. Well, there is a limit theorem for averages, and we would say that xn bar converges in probability to a limit, and we relate this back to the ordinary definition of limit by saying, well, the probability that x is closer than any specific distance converges to 1. So in this case, probability xn bar minus the limit being less than any quantity epsilon that you fix, then that probability is a number, Pn, right? And the definition of convergence in probability is that sequence of numbers, Pn, converges to 1, right? So we've converted the problem of what does it mean for a random variable to converge? We've converted that back to the definition of convergence of a series of numbers. We've said convergence in probability implies a convergence of the collection of probability numbers in the standard sense of the definition of convergence. So now we have a way of talking about how random variables converge. So establishing that a random sequence of variables actually converges is hard. As you can imagine, it's hard. If you look back at the previous definition, it's not the easiest thing in the world to think about. So we have something that makes it a lot easier for us, and that's called the law of large numbers. So if you've heard people talk about the law of averages, typically they don't know what they're talking about, but probably they're referring to the law of large numbers. And the law of averages, or the law of large numbers, basically says that if xn to x1 are IID from a population with mean mu and variance sigma squared, so in this case we're going to assume that the random variables have a variance. It's interesting to note that there are distributions where there is no variance. You try and calculate the variance and you get infinity or something like that. In this case, we're going to assume that there is a variance and that it's finite. Then the sample average of IID observations always converges in probability to mu. And that's called the law of large numbers. Probabilists make a lot of distinction over various kinds of the laws of large numbers, and they've worked very, very hard to get kind of minimal assumptions for the law of large numbers to work. And in fact, we're using a very lazy version of the law of large numbers. They would probably be upset at us for teaching this one, but it's okay. We don't care. The basic idea I want you to get is that averages converge to mu. Averages of IID observations converge to mu, the population mean from which the observations were drawn. This is a good thing, right? This basically says if we go to the trouble of collecting an infinite amount of data, then we get the number that we want to estimate, mu, exactly, right? Which is good because collecting an infinite amount of data takes a lot of time, actually infinite amount of time. If you're willing to make this many assumptions, the x's all have a finite variance, it's pretty easy to prove the law of large numbers using Chebyshev's inequality, which Chebyshev's inequality, if you remember, had a pretty simple little proof. So this kind of very complicated idea, it's amazing that it has a fairly simple little proof. So remember that Chebyshev's inequality states that the probability that a random variable is more than k standard deviations from the mean is less than 1 over k squared. So therefore, the probability that xn bar minus mu in absolute value is bigger than or equal to k standard deviation of x bar sub n is less than or equal to 1 over k squared. Now, let's pick an epsilon. Pick any distance epsilon, because remember, to establish the convergence of a limit of numbers, we have to pick an epsilon. And now to establish convergence and probability, we have to show that the probability that xn bar minus mu being bigger than epsilon goes to 0, or being less than epsilon goes to 1. Those two statements are equivalent. And so let's let k from our previous definition be epsilon divided by standard deviation of xn bar. K is not a random variable, right? Epsilon is a number that we pick, and standard deviation of xn bar is a random variable, but the standard deviation of it is sigma over square root n, okay? So this is just a number. There's nothing random in our definition of k. So if you plug that back in for k, right, you get the probability that xn bar minus mu being bigger than epsilon is less than or equal to the standard deviation of xn bar squared, which is the variance of xn bar, divided by epsilon squared. And we, from a previous lecture, already calculated what the variance of xn bar is. It's sigma squared over n. So this probability is less than or equal to sigma squared over n epsilon squared. Now, as n goes to infinity, sigma squared isn't changing and epsilon squared isn't changing, and the n's in the denominator, so this whole thing goes to 0. Okay, so the probability that the random average xn bar is more than epsilon away from the mean goes to 0 as n goes to infinity, or restated, the probability that xn bar is less than epsilon from the mean goes to 1 as n goes to infinity. So in either of those statements equivalently say that xn bar converges in probability to mu. I think it's kind of staggering that it's really basically 2 lines is all you need to establish this fairly complicated result. Now on the next page, I just have a simple example where I simulated random normals with a mean of 0, and I show the cumulative sample mean. So I took one random normal, and then I took that random normal and generated a second random normal, and then averaged it, and then generated a third random normal, and just averaged it with the remainder. And the iteration on the bottom is the number of observations that goes into that mean, right? And then on the vertical axis, it shows the value of the average. And you can see at first there's quite a bit of variability, right? Remember, the variance of the average is sigma squared over n, so the variability is going to 0, and this dashed line is the asymptote, right? And as you can see, this average, as we include more observations in it, is going to converge to this. You can see it already converging a little bit by 100 iterations to this dashed line. That's simply the law of large numbers. So let's cover some useful facts about the law of large numbers. One interesting fact is functions of convergent random sequences converge to the function evaluated at the limit. So this includes sums, products, differences. So for example, xm bar squared converges to mu squared, right? Because x bar converges to mu, and so this is just a function of x bar, so xn bar squared converges to mu squared. Something different is that average of the squared observations converges to a different entity, okay, right? Let's go through this a little bit carefully just because it's kind of an odd little point. So xm bar squared converges to mu squared, but if we sum up xi squared, the individual observation squared, and divide it by n, that no longer converges to mu squared. Well, why not? Well, it's the difference between the square of the average and the average of the squares. So in this case, it's the average of the squares. In this case, each xi squared is a random variable. So we could just call it y instead of xi squared. And then their average of these xi squareds, or average of these y's, is going to converge to the population mean of those y's. Well, we can calculate that. We know what the expected value of xi squared is because we can use the shortcut formula for the variance, which recall was expected value of xi squared minus expected value of xi quantity squared. We can just work that formula to solve for expected value of xi squared and show that that's equal to sigma squared plus mu squared. So the average of the squared observations converges to sigma squared plus mu squared, whereas the square of the average converges to mu squared. So it's kind of an interesting little point, but just remember that those things are different. And by the way, this little fact that we just showed, we can use this to prove that the sample variance converges to sigma squared. And we'll do that on the next slide. So let's actually go through this proof that the sample average converges to sigma squared. And I think you'll see in the process of the proof that it doesn't matter whether we divide by n or n minus 1, it's going to converge to sigma squared. So here we have the definition of the sample average. Summation xi minus xm bar squared, all divided by n minus 1. We're going to use the unbiased estimate of the sample variance. Well, recall there was a shortcut formula for the sample variance, and it worked out to then be the numerator had a shortcut formula that was summation xi squared minus n x bar squared. And so we're going to use that formula, and then we get summation xi squared over n minus 1 minus n bar squared over n minus 1. And let's just rearrange terms and multiply and divide by some n's because that n minus 1 is a little annoying. So we have n over n minus 1 times summation xi squared over n minus n over n minus 1 times xm bar squared. Well, let's look at each of these things in turn. And remember, from the previous slide, I told you, I didn't prove this and just have to take it as true, is that, if you multiply convergent sequences, they converge to the product of the limits. If you add and subtract convergent sequences, they converge to the difference of the limits and so on. So let's look at each of these terms one at a time. N over n minus 1, clearly that converges to 1. If you don't believe me, plug n over n minus 1 in for a very big value of n in your computer, and you'll see that it gets closer and closer to 1. Probably the easiest way to see this is it's 1 over 1 minus 1 over n, and that 1 over n clearly goes to 0. Okay, we just on the previous slide talked about how summation xi squared over n converges to sigma squared plus mu squared. So the second term converges to sigma squared plus mu squared. Then we have minus n over n minus 1, which again converges to 1. And then xm bar squared converges to mu squared. We talked about that on the previous slide. So we have this expression right here, sigma squared plus mu squared minus mu squared, which is just sigma squared. So that proves that the sample variance converges to sigma squared. And then, of course, the sample variance, if we happen to divide by the biased sample variance, if we happen to divide by n instead of n minus 1, also converges to sigma squared. And then we can square root the sample variance and get the sample standard deviation and see that it converges to sigma as well, just by the rule from the previous page where we said that functions, in this case the square root function of convergent random variables, converge to the function of the limit. So what we've found is we have our law of large numbers, and with a couple of rules that we just stipulated, we've got that the sample mean of IID random variables converges to the population mean that it's trying to estimate. The sample variance converges to the population variance that it's trying to estimate. The sample standard deviation converges to the population standard deviation that it's trying to estimate. And in all these cases, you see the pattern that the sample entity converges to the population quantity that it's trying to estimate, basically saying that if you go to the trouble of collecting an infinite amount of data, then you actually get the value that you want to estimate. You don't get it with noise, you get the actual value. We give this name a property, and we say that an estimator is consistent if it converges to what you want to estimate. And the law of large numbers is basically saying that the sample mean is consistent. And then we now know that the sample variance and the sample standard deviation are consistent, and it doesn't matter whether you're dividing by n or n-1, they're all consistent. But also remember that the sample mean and the sample variance are unbiased as well. And by the way, the sample standard deviation is not unbiased. Consistency, by the way, is a very weak property. So the sample standard deviation is biased, unlike the sample mean and the sample variance. Consistency is a very weak property. Saying that an estimator is consistent is not even really a necessary property. It seems like it should be necessary, but if something converges to mu plus epsilon, where epsilon is a minuscule number that is of no importance, then that estimator is not consistent. So it's fair to say that consistency is sort of a kind of a weakly necessary, but definitely not sufficient property for an estimator to be useful. We've also seen that being unbiased is neither necessary nor sufficient for an estimator to be useful either. For example, we talked about the bias variance trade-off, that estimators can be slightly biased, and you can want that because you improve on the variance. So what we're winding up with is a collection of properties that describe estimators, and you really need to think about the collection of properties as a whole to evaluate an estimator. And these various mathematical concepts are useful, but they never in isolation tell the full story on the utility of an estimator. They might be useful for eliminating really dumb things. If something's definitely not consistent in a way that it doesn't converge anywhere near the estimate, probably that's not something that you want to use. But apart from those kind of stark circumstances, these properties you need to take as a collection to try and decide which estimators are the right ones to use. So let me give an example of an estimator that's consistent but not very good. So take the data and only take the first half of the collected observations. So we have, instead of xn bar, we have xn over 2 bar, right? That estimator is, of course, consistent as n goes to infinity. It just has fewer observations than if you took all of them, but still the n is going to infinity. In this case, it's just n over 2. So that estimator is consistent, but it's got an obvious better estimator right in front of you, basically the estimator using all of the data. So there's a particular example of an estimator that's not consistent, where there's a better estimator that comes to mind. Here you have to actually account for the fact that the estimate with all of the data has a lower variance than the estimate with half of the data. So that's enough discussion of limits and the law of large numbers. Next, we're going to go on to the central limit theorem, a very important theorem in statistics.